And even though the truss model, it is called truss model to simulate the behavior of a concrete section for the shear actions, is not very new. It's old, but still it is used in different codes, including Eurocode. And the idea is that it simulates the shear behavior of a reinforced concrete section by a hypothetical virtual truss structure like this. You can see, and for example, if you focus on these two diagonal elements, after applying a vertical load like this 2V, these are the reactions for in a simple beam. We are discussing this. And based on the deflection, because the bottom line will be in tension and the top line is in compression, which means that the element AB will lose some lengths, but the element CD will gain some lengths. So the element CD will be in tension and element AB will be in compression. And this, if you don't have any reinforcement to carry these loads, there will be some sort of shear cracking near and close to the support like this. And you can see that the shear cracks are along with the forces of element CD, which is in tension. So is in tension there will be some cracks, which we anticipate that because concrete is awful in tension without reinforcement, as of course. So in tension, the concrete strength and tension is really low, and with a touch of tension, it will produce cracks. So that's why when you put some transversal shear reinforcement, you can some sort of transfer these shear forces to those transversal shear reinforcement, and they will bear these kind of shear forces. That's the whole idea. I don't want to get more in details into the theory, and I prefer to go through the application in Eurocode. The general idea is that uh, uh, a part of the shear force can be carried by concrete, and another part, the rest, can be carried by steel. This is the common practice in most of the codes around the world, like the American code, ACI. But one of the most differences between the American code and Eurocode is when we are designing for the shear actions in Eurocode, we do not rely on uh, concrete contribution to carrying shear forces. For example, if you have something to be designed, some shear forces to be designed, you should allocate all of the shear forces to the reinforcement. This is uh, the probably most highlighted difference between the American code and Eurocode. So, although we have some situations that in some regions, in some members, the shear force, the resultant shear force from structure analysis is still less than this value, VRDC. VRDC, it means V stands for shear force, R means resistance, D means design, and C means concrete. So this is the shear force, the resistant shear force from the concrete. And if the resultant shear force from structure analysis from ETABS is less than this value, there is no point to design for shear forces. Although you always have some minimum shear reinforcement to be there in place. But if you're less than VRDC, it's fine not to design your section for shear forces. But if you're more than this value, you have to design for the shear forces. You always need to check for the minimum reinforcement, but you have to design for the shear forces. And for that design, you need to allocate all of the shear forces to the reinforcement and forget about having VRDC. So if VED, the resultant shear force, is more than VRDC, then we'll just put VRDC aside. We don't rely on that, and we just design our section for the resultant external forces, VED. So we continue with this in the Eurocode with the equation 6.2, which gives you the VRC just to see if we are less than that or more than that. And the parameters are defined here. They are really straightforward. Rho L is the ratio of the longitudinal area over the section area, and K is calculated by this simple formula, should be less than 2. D is the effective depth, BW is the smallest width, which in the case of rectangular section is the width, and sigma CP is coming from axial forces, which usually is 0. So this term is 0, and do not bother yourself with this, because in most cases, really, not always, but really in 99% of the cases, in both beams and slabs, you don't have really axial forces. So in some exceptional cases, like if you have flexible diaphragms, you may have some axial forces, considerable axial forces in beams or slabs, which means that you need to calculate for this term as well. But this is a sort of helping term. So if you're neglecting this term, you're in the conservative side because it's adding to the first term. So um, if you neglect that part, you can simplify the formula like this, and you can imagine this is the minimum. This formula, you can calculate this one, but this VRDC should be more than this term in the right hand side as well. Sometimes the second term governs, as you will see in one example in the later slides. For example, just to have some impression from this formula, I just adopted the example 6.6 from the last sessions. We had this example from the book, and the idea was to design this section for this slab for flexural moments. And if you remember, the thickness was 300 millimeter. So if you remember, I told you the 300 millimeters is sort of too much for this case. And also, if you remember, uh, the flexural design resulted in some sort of longitudinal reinforcement, which was coming from the minimum requirements rather than the actual formula. So it means that the 300 millimeter was some sort of too much for that, and we could have a smaller values for this slab thickness. Anyway, we are not changing anything here. We are just calculating the parameter of V. Where is it? VRDC, and I just wrote every single parameter here based on this example. Just go and check we had all the parameters here, and I calculated VRDC DC as 102 kilonewton. And also I checked it with the second formula that VRDC should be more or equal than that. And I got 129 kilonewton. And again, you see that these two formulas are, the first one is this one, and the second one is this one. And as you see, the second formula governs the case here, which means that it means again that the 300 millimeter thickness is too much for this case. Anyway, based on the Eurocode, the VRDC is 129, almost 130 kilonewton. It means that I calculated everything for 1 meter length of the slab. So uh, if you really from ETABS or whatever analysis you're using, if in a 1 meter slab, if you have the shear forces less than 129 kilonewton, it means that you don't need the shear design. That's the point. And if the uh, resultant analysis gives you more than 129 kilonewton in 1 meter of your slab, it means that you have to go to design your slab for the shear forces, although you're neglecting this amount of shear capacity from the concrete. However, if the resultant analysis shear force is less than 129, still you need minimum reinforcement for the shear. Always you need to check the minimum reinforcement. So again, I elaborated a little bit more with the same example, and I assume that, okay, my shear forces from structural analysis is less than 129 kilonewton, and I don't need to design for shear forces. However, I need to consider the minimum shear reinforcement. So this is the calculation for the minimum shear reinforcement based on equation 95N from Eurocode and 2, and the minimum ASW over S. ASW is the shear reinforcement area, and S is the spacing between them. The minimum for this is provided with this simple formula. You need to have FCK, which is 30 megapascal, and FYWK, which is 500 megapascal, and the spacing should be always less than 75% of the effective depth D. So I calculated this formula and I came up with 0.85 for this ratio, the minimum for this ratio. So for now, I just calculated the spacing like 75% of 265, which was the effective depth here. So I came up with something like almost 20 centimeter. And as a designer, you need to choose what do you want to use. For the shear reinforcement, we really use reinforcement number 6 or 8, not more. Really, it should be fine for all the sections, either 6 or 8. And in very rare situations, you use number 10, but usually you should be able to design your section by H6 or H8. So I'm using H6 at every 150 millimeter, just to be less than 198. So I don't want to round it up because I need to be less than this. So 150 is a round number, which makes the construction easy as well. So if I use in 1 meter, I'm working in 1 meter. So if I put every 150 millimeter one shear reinforcement, I can place 7 reinforcement number 6 in 1 meter slab lengths, which means I will have the total area of 197.82 square millimeter. And if you calculate, put this instead of ASW, and S is 100, S is 150 millimeter. So you will come up with this ratio, and you can say this ratio is more than this one that I needed to be. It was meant to be the minimum. So now I'm quite more than that, and that's okay. So we are more than fine for the minimum reinforcement. So we need to put uh, only one layer of shear reinforcement at the top of, sorry, we'll put the shear reinforcement here at the top of longitudinal reinforcement, and we'll continue this to the end, and we'll bend it like this. So we don't have, please note that we don't have 2 layers of shear reinforcement in slabs like this. We only have 1 layer at the top, perpendicular to the longitudinal reinforcement. All right. But there is another uh, point to mention. Here we have 1 layer of shear reinforcement, and that's why when I'm using this area, I'm calculating this area here, I'm just assuming 7 uh, reinforcement number 6 in 1 meter, right? But in the case of beams, when we go further, when you have some longitudinal reinforcement at the top and bottom, and you use a surrounded shear reinforcement, you need to calculate both of these legs to calculate ASW. That's the difference. So if you have a complete surrounded shear reinforcement, number 6, you need to double the section. I will mention to it later on in the other examples. So this is some description of the truss model from the book. I strongly recommend to read the book in this part. For this part, it will give you some insight into the problem as well. And I want to recall you that we had this discussion from uh, from the structural design module last year, but probably you have forgotten some parts, but that's fine. Uh, if you, I provided the Excel file for you. This is coming from structural design as well. If you remember, I've designed this Excel file for structural design, and it had 4 sheets: case 1, 2, 3, and minimum ASW. The minimum ASW, you can imagine, is the minimum reinforcement you need to check in any case of design. But case 1, 2, 3 are for 3 different cases that may occur during the process of shear design. And the whole idea is for the beginning of your shear design, you need to calculate 2 parameters, V max 2, V max 1. Can you see this? Which connects this blue curve from the start to end. So for each section, we can calculate V max 1 and V max 2. And the important thing is the design shear force, which comes from ETABS or structure analysis, can have 3 situations when you compare it with these 2 values, Vmax1 and Vmax2. So in the case number 1, this green line is the VRD max, which means that the shear force coming from ETABS, from structure analysis, okay? So the VRD max can be more than both of them. In the case 2, can be less than both of them. In case 3, can be somewhere between both of them, right? So this is These are the three cases that potentially you can face, and there cannot be any other cases when you compare a single value which comes from ETABS to these two values, max 1 and max 2. So in the case that in the case number 2, that um, in the case number 1, when it is more than uh, max 2, it means that you don't have any option rather than increasing your section area. Otherwise, or yeah, the concrete will crush. So it's the case that you need to figure out how you can increase your section. But in the case 2 and case 3, you need just to calculate an angle, which is called theta. And with that theta, you can come up with your shear design process, which is illustrated in the Excel, and also I will illustrate it here in the lectures. So there are principally three cases, case 1, 2, and 3. And as you can see, in case number 1, if the ETABS is more than max 2, you need to increase the section size. In case 2, if it's less than max 1, which means that obviously it will be less than max 2 as well, it means that you need to calculate theta from this formula, and or and finally you can design your section like this. And in case 3, if the VED is between these two, sorry, if it's more than, in the case 2, if it's less than max 1, the theta is 21.8 degrees, which means the cotangent of theta is 2.5, simple and pure. But in the case 3, when the ETABS shear force is between max 1 and max 2, you need just to go through the formula for calculating theta, and after that you can design your shear reinforcement with this simple formula. That's all. And this is the spacing, which forget about this term, just use this one for vertical shear reinforcement, which is always the case in practical design. So I also provided the Vmax 1 and 2 here. At the start, you need to calculate Vmax 1 and 2 just to see which case your case is. And that's the whole process. You need to take one of these cases for your shear design. So you can either use the Excel for your design, or do it manually. And there are a few examples in the book just to discuss this. How does it work in real practice? So we just forward to example 610, which is the shear link beam number 1. A simply supported rectangular beam is shown in this figure, and using the data, determine the required area of shear reinforcement based on the distance d from the support. So another point is that when you're designing a sort of beam, which is, for example, this is the support, and this is a simple beam laying on this support, all right? When you want to design for the shear forces, the code enforces you to design for this section, which is at a distance d from the face of the support. This is the face of the support. So if you design for this one, this section, the shear force is more than this section, but you're getting some discount somehow. But the critical section for the shear design is here at a distance d from the face of the support. So we'll see this in one of the examples here. So uh, there are some data to be used here, like the previous examples. And the idea is that the VED, the shear force, should be calculated based on this uh, uniformly distributed force along a single beam, and the length of the single beam is provided here, 7.8 meter, and the effective span of the beam is 8 meters, so it means that you have 20 centimeter in each end for your beam to lay down on the support. So that's why uh, the shear force is calculated based on 8 meter, which gives you 120 kilonewton, but the effective length is 50 centimeter less than the 8 meter, which means that you have 25 centimeter in each end laying down on the support. So it means that you need to reduce the shear force by this proportion, and you will get 111 at the face of the support, and you need to go at a distance of d, and which means that you need to further decrease the shear force from 112 to this value, 100.8 kilonewton, to be at a distance d from the face of the support. We can discuss this during the next lecture as well to see how does it work. When you come up with this value for your shear design, you need to calculate VRD max 2 and max 1, and they are 407 and 590. So as you see, your design value, which is 100, is less than both of them. So you are in the case number um, we are in the case number 2 among this slide. So you simply take your cotangent theta equal to 2.5 and put it in the formula, and you will get the ASW over S, and the maximum spacing is 75% of D, which means 29 centimeters. So we assume we will put shear reinforcement in every 275 millimeter. So assume two-legged 8 millimeter diameter link. It means that when we have a surrounded shear force, we have two leg, 1, 2. So that's why we are multiplying the area by 2. And so we are using reinforcement number 8 for every 275 millimeter. So this is the shear design for this section. And for the next example, a concrete beam again is simply supported over an effective span of 5 meter, as shown in this figure. So there are 3 steps to take into account, and it says that verify the shear resistance at the face of the support. So for the first part, it is just calculation of the external forces. This is the structure analysis. You need to be able to follow this. Otherwise, if you have problem, we can discuss this in the next section. And suitable at a distance d from the support. So it means that this is, this is the wall, this is the wall, this is the face of the support, and you need to design for the shear reinforcement here at a distance of d from the face of the support. And that's why finally you will design at a distance of d, the shear force will be 26 kilonewton. Again, when you know what is the force for the design, you need to calculate max 1 and max 2. In this case, it is 200 something and 100 something. Again, you are in case number 2, the cotangent theta is 2.5, and it's very straightforward to design your shear reinforcement, which will be number 8 in each 15 centimeter. So we just proceed to the example 612. So just a few parameters are different here, but really it's straightforward. Again, you're in the case number 2. Just try to review the example, and we will discuss any doubt or problem during the next session. Here is the distribution of the shear forces along the beam. Do you remember in last session I came up with some distribution of shear forces for some sort of beam? It is some sort of similar problem, and the distribution of shear force is linear always for uniformly distributed loads on the beam, on a simple beam. So you need to, if you like, you can draw the diagram, and then getting at a distance of d, you will come up with this value for the shear design. So what I'm proposing is to go through the different slides here and also read the book for the shear design. And for the next session on the 1st of December, Friday, we will go through a brief discussion about the shear design. And after a brief discussion, questions regarding the shear design, if you have any, we will have a sort of quiz competition about the shear design. I will reveal a question for the shear design, and you will have half an hour to solve it. And there will be a potential prize of 5 extra marks for your coursework if you can demonstrate that you have get the final answer. So that's the program for the next session. And thank you very much for your listening.